Excuse me, but I would like to know, where did all of those symbols come from in calculus? There's so many of them. I don't get it. What's going on? Mama Llama's back with another great math question. Oh, she's small. There we go. Yeah, thank you, Mama Llama. That is such a great question. Okay, so calculus has got a lot of symbols. And sometimes you're like, why are there so many symbols? Do they mean the same things? Do they mean different things? Is it just a matter of opinion? Well, let's dig into it. Okay, we're going to focus on derivative calculus because I feel like, where a lot of the confusion comes from. So there's actually lots of different ways to write the symbol for how to take a derivative. Probably the one that you have seen the most is this pretty lady. Oops, we'll do dy dx. So this is for a first derivative. But you can also write the exact same thing with a capital D, a subscript x, and a y. You might also see y dot, although this one's a little different. We'll talk about that in a sec. And you may also see y prime. Holy stars, that's a lot of different notations. But all of these are first derivatives. Yeah, first derivatives. For second derivatives, each of these has its own subsequent notation. So for our lovely friend dy dx, you would see d squared y, dx squared. For our capital buddy, you would see d squared with a superscript, subscript x, acting on y. For our dot notation, you would see a double dot. See, look, it's like a smiley face. And for prime notation, you'd see a double prime. And these are for second derivatives. Second derivatives. Dervs. We'll say dervs for short. Okay, so what the heck? 4 different ways to write the same thing? What is going on here? Let's break it down. So, I'm going to get another color too. Fun. Okay, let's go for green. So this first set of notation is actually from Leibniz. And Newton and Leibniz discovered calculus around the same time, separately, and then they had a big argument about who did it first, because so it goes. Newton kind of gets the name credit, but turns out we actually use Leibniz's notation pretty frequently. Why? Because it's pretty clear what's going on. We have an operator, d dx, that acts on a function, y, or you could say, a function f of y or f of whatever variable that you want. And so this is pretty clear what variable we are taking the derivative with respect to, x, this buddy right here, and also what variable or what function we are acting on, which is this y right here. And so this notation is really helpful for folks just learning calculus because it's a little bit easier to understand what the operation is. Just like when we learn early on in mathematics that this is not a t, it is a plus, that this is a minus sign, and we learn how to take the operations given by these symbols. When we get to calculus, we have to learn how to take the operations given by these symbols. And these are all different symbols to really express the same thing. And so we might see them in different contexts depending on what we're doing. Okay, so we got Leibniz's notation. What's up with all these other ones? I'm going to skip around a little bit. Let's go to the dot notation. We'll use blue for this one. So the dot notation is actually from Newton. And the difference here is that this tends to refer to, well, I should say, yes, it refers to time derivatives. So where we are taking the derivative with respect to t. So in other words, if we're going to cheat and use Leibniz's notation, this would actually be dy dt equals y dot. This is a code speak for this is equal the same thing as this. And the double dot is just the second derivative. So the reason why we might use this, I've used this a lot in physics when I did all of the different problem sets in physics, and sometimes in engineering too, because we like to be lazy. This is a lot faster to write than dy dt. And since this symbol is commonplace, slash we learn it as we learn calculus, we know what we are doing with the dot because our teachers teach us, and then we know how to take the operation or how to work with that. Okay, Newton, so you did get some notation in here. It just has to do with time derivatives. All right, and finally, what about these other buddies? So let's see, let's do this one first. So the capital dxy and d squared x are from Lagrange. And Lagrange was a bit later after Newton and Leibniz. I think they were 16th century and Lagrange was 18th century. Don't quote me on that. My math is better than my history. So, excuse me. I'm getting over a little cold, so I got a little cough. But the reason why we might use these is if we're dealing with a more advanced calculus. So if we're dealing with differential equations and particularly partial derivatives, which we haven't even looked at yet, we might want to use this notation because it's pretty clear what variable you're acting on and also what function you're acting on. So whereas the dot notation or even the prime notation might be a little bit unclear what derivative you're taking, what variable you're taking the derivative with respect to, or whether it's a partial or a full derivative. The prime notation doesn't tell you that, but this notation does. So yay for clarity. And finally, we will use orange for this last one. The prime notation was, I believe, invented by Euler, but popularized by Lagrange. Again, big name in mathematics. That was a smart cookie. So the prime notation is really helpful if you want to be lazy and if you're working with high order derivatives, because you can quickly write, for example, the nth derivative of a function. And yes, maybe you will get up to very high orders of derivatives. You can do the same with the capital ones. I'm cheating with my orange. You could say dnx of y, but this is a bit faster. So if you want to be lazy and quick, you can just use this notation. But if you're dealing with partials, you probably want to use this notation. Okay, and finally, I alluded to it, but we didn't quite look at it yet. What in the stars is the difference? Ooh, let's use a different color because I can. Ha ha ha, yellow. What in the stars is the difference with this curly d, dy, this curly x? Is that a 6? No, it's a curly d. So this is a partial derivative. And what you will probably see, partial derv, okay. What you will probably see instead of y is a function of x and y, or maybe more variables. And the reason why we have this notation versus our regular handy-dandy d is because we will effectively treat all of the other variables in this function as constant, and we will take the derivative with respect to this one variable. Partials are much easier to calculate than full derivatives if you are dealing with a function of multiple variables. And so this is another tool in our toolbox, another operator for us to use to solve equations and maybe learn some things about the universe around us. Okay, so there are a lot of symbols in my bag of calculus tricks. The TLDR is that they come from different folks who have worked to build out our, theory of calculus, and they are used for different applications. But fundamentally, there's lots of different operators to mean the same thing. It just depends on, maybe you have a different preference, or maybe you are working in a different application and one notation is going to be more useful so that you don't drop certain things or do the wrong operation. So use the one that works for your application and that feels right to you, except for the time one. Make sure you're doing time derivatives. Okay, thank you very much for hanging out with me and learning more about the wonderful world of calculus and mathematics. Please let me know if you have any questions, and we'll see you next time, friends. Goodbye!